Welcome everyone. Thank you for attending this session. In this session, we have the presentation of Mehrdad Farajtabar from Google DeepMind. Let's have a quick biography. Mehrdad is a researcher scientist in Google DeepMind working on machine learning and applications. His recent research interests are continual learning of neural networks, learning under evolving data distribution, and reinforcement learning. Before joining DeepMind, he graduated with PhD in computational science and engineering from Georgia Tech in 2018 and holds MSc and BSc degrees in artificial intelligence and software engineering from Sharif University of Technology. All right. In this session, he will talk about dealing with catastrophic forgetting in continual learning of neural networks. As you probably know from previous sessions, the talk is a recorded video. After the talk, we will have Mehrdad for Q&A. You can ask your questions in the comments. We will go through them after the talk. Okay, here is the presentation.
Hi, I'm Mehrdad Farajtabar, and I will be giving this talk on continual learning and overcoming catastrophic forgetting in neural networks. So this talk will be started with an introduction to continual learning, followed by an exposition to the catastrophic forgetting problem. Then I will introduce a few methods to tackle this problem. The first one is a regularization-based scheme that uses orthogonal gradients to preserve past knowledge. The second method implicitly creates gates or pathways to forward and backward propagate task signals. The third one investigates the neural network training regimes and their implications towards continual learning. And finally, I briefly study how modeling loss function can be leveraged to overcome catastrophic forgetting. But before that, an introduction to AI and neural networks. Artificial intelligence could be humanity's most useful invention. It's because by solving this single problem, we probably can unlock solutions to thousands more. Towards achieving AGI and solving this grand challenge, artificial neural networks are the main building blocks. They mimic the structure of the human brain and consist of multiple layers of processing input signals to fit a pattern or approximation or approximate a function to perform a cognitive task. For example, they can be used to solve a classification task, like classifying or distinguishing digits in handwritten digit images. We will use this running example through this talk. In real world, we need to deploy these machine learning models over a course of time where we're not allowed or it's not feasible to go over previous data again and again. Therefore, we need to equip our AI agents with the ability to learn continuously, which is a critical component of intelligence. It's the case when new information is constantly available, but previously presented information is unavailable to retrieve. Ideally, an intelligent agent should be able to learn consecutive tasks without degrading its performance on those already learned. This could be different cognitive problems like image classification or face recognition, or even natural language processing or voice processing. A continual learning solution for deep neural networks may involve techniques to deal with various problems. That's what we call the desiderata for continual learning. Like this can be, for example, being able to better transfer to new unseen task, which is called forward transfer, or improving over the previous task after learning new task, which is usually referred to as backward transfer. Task identification or task boundary detection is also a relevant subproblem. Note that we even may not have an explicit notion of a task. However, one of the most important challenges of continual learning is catastrophic forgetting, where we witness a degraded performance on previously trained tasks if the model could not revisit their data. There is an implicit assumption in continual learning that the previous task may happen again, for example, in a recurring or in a seasonal manner, or at least they have relevant information for future tasks and remembering them is necessary. A neural network has the capacity to memorize all the data or master all the previous tasks if they are available simultaneously, but their knowledge is very plastic and can be overwritten easily if we go to new tasks without access to previous ones. That's the catastrophic forgetting problem, and that's the subject of this presentation. So let's see how catastrophic is this problem. So a rotated MNIST is a simple yet unresolved benchmark for continual learning. Here, each task is to distinguish the same classes with the input images rotated by a specified degree. For example, task 1 is all the MNIST images, task 2 is all the MNIST images with the same labels, but all the images have been rotated by 10 degrees, and so on until task 4. So before introducing the forgetting problem or seeing how catastrophic it is, let's first see how related are these tasks and how a neural network can generalize. A two-layer MLP, multi-layer perceptron network, trained on task 1 and that achieves high accuracy on task 1 cannot generalize to a slightly rotated dataset. Two-layer MLP is a very simple network. However, this pattern is so easy that a 3-year-old toddler can easily master it. But neural networks can't. At least this simple neural network can't. So neural network generalization is a hot and trending topic of research and is not subject of this talk. Let's first deal with the simpler problem that neural networks are not able to handle previously learned task or previously seen data, and then tackle the generalization problem. Now, let's get back to our problem. Training tasks sequentially from task 1 to task 5 and measuring how much we forget the previous task or how much we forget task 1, for example. So task 1 reaches accuracy over 95% right after it's being trained. However, as we train more tasks, it starts to forget until around 67%. And that's almost forgetting 30% of the data. Therefore, forgetting is really catastrophic. The accuracy falls down to 67% after being trained on 4 tasks and 4 almost similar tasks. Humans never forget like this, or never forget this fast like this. And remember, rotated MNIST is a very simple task. So if we want to achieve AGI, artificial general intelligence, we need to alleviate this shortcoming. Neural networks, again, have the capacity to master all of them if they are able to see all the data simultaneously. But for example, when being trained on all of them, or in a multitask learning setting, but when they are trained sequentially, their network is so plastic and they forget the previous one this easily. So there are many families of solutions to tackle this problem, from rehearsal or replay-based methods to regularization ones. And there are also various ways to make a taxonomy of continual learning methods. But let's quickly review a few the few main families of the continual learning solutions. The repetition or replay or rehearsal based methods employ memory systems that store previous data or alternatively train a generative model for the previous task and replay the data interleaved with samples drawn from the new task. So replaying the previous data is obviously the first solution, or replaying a sample of previous data. But these methods are usually they need a lot of memory, and they may risk privacy of users, and in many applications it's not feasible to go over previous data again and again. The expansion-based methods allocate new neurons or layers or modules or whatever to accommodate new tasks while utilizing the shared representation learned from previous ones. These methods may be too complex for the current neural network systems or libraries. And finally, the regularization-based approaches. Uh, in this in these methods, catastrophic forgetting is usually tackled by imposing constraints on the weight updates of the neural network according to some importance measures for previous tasks. And the difference lies in the way how importance weights are computed. So, as the first idea, I'll present a method based on regularization to tackle this problem. And here is the reference to the paper if you want more details. One probable reason for catastrophic forgetting is that neural networks are usually trained by stochastic gradient descent or its many variants, where the optimizers produce gradients that are oblivious to past knowledge. These optimizers, by design, produce gradients that are purely a function of the current mini-batch or some smooth average of a short window of them. This is a desirable feature when the training data is IID, but is not desirable when the training distribution shifts over time. So the core idea of our approach, called orthogonal gradient descent, or OGD for short, is to preserve the previously acquired knowledge by maintaining a space consisting of the gradient directions of the neural network predictions on previous tasks. Any update orthogonal to this gradient space change the output of the network minimally. When training on a new task, OGD projects the loss gradients of new samples perpendicular to this gradient space before applying back propagation. An important feature of our approach is that it doesn't need to store the previous data that might be risky or risking privacy, or we may not have the sufficient memory. So here we want to present the main idea of the paper, and please refer to the paper for the mathematical details. Imagine a function fj in the parameter space w star associated with the j's logit of the neural network. So j's logit would be the proportion that this example belongs to the class J. For simplicity here, W star is a two-dimensional. We can see that the level curves in which this function, that is the neural network prediction, does not vary. The gradient of the function with respect to the parameter W is directing towards perpendicular to the tangent line or tangent space. And it's it's corresponding to the direction with the maximum change locally. And moving perpendicular to this gradient is associated to the minimum change, again locally. So the blue direction is the direction that is associated to the minimum change, but the green direction is associated with the maximum change to fj. So this is the idea that we're going to build our work upon. Note that, and moving perpendicular to this gradient is associated to the minimum change, again locally. So the blue direction is the direction that is associated to the minimum change, but the green direction is associated with the maximum change to fj. So this is the idea that we're going to build our work upon. Note that, in contrast to many recent works that constrain the loss function, here we regularize or constrain the neural network predictions directly, not the loss function. Because in modern neural networks, where the network is usually over-parameterized or the training regime is near interpolating, that is, the training error tends to go to zero, the loss can vanish, and therefore it may not be a good medium to preserve previous information. But fj does preserve its meaning, even when the training error is almost zero. So that's why we choose to work with the neural network predictions, not the loss. So now back to mitigating the catastrophic forgetting problem. Assume we have already optimized for task A and reached to a good parameter W star A. Task 2 arrives and our goal is to find a new solution. Because of the over-parameterization, we usually can find a solution near the solution of task A that is also good for task B. And also, it's the case for an optimum for both tasks. This is also an assumption in many continual learning papers, like EWC, which I introduced later, or those papers based on synaptic consolidation and regularization. If we run a stochastic gradient descent, it will be oblivious to past knowledge and reaches to a point that is best for task B alone, forgetting all the information that the machine has learned so far for task A. But OGD considers the space S an orthogonal space of previous model gradients. Now assume we are going to run SGD. Assume G is the gradient of the loss on the new data, or a mini batch of data. OGD first projects G into space S. The gray dotted line is its projection. Then, by subtracting the projection from the original gradient, we got G tilde. So we can show that G tilde is still a descent direction, meaning that it minimizes the loss over task B. Additionally, it changed the output of neural network on task A minimally. So this procedure repeats until we converge, potentially and hopefully to a point that is good for both tasks. For the details of the proposed method, please refer to the paper. So we also empirically validated the proposed method on common benchmarks. In our experiment, we've used a ReLU network with 2 layers. Each of them has 100 neurons. And for each task, the model is trained 5 epochs with a fixed learning rate of 10 to the minus 3. We've compared OGD with a few important baselines. EWC, or elastic weight consolidation, is one of the pioneering regularization-based methods by DeepMind that uses Fisher information diagonals as importance weights. AGEM, which uses loss gradients of stored previous data in an equality constraint optimization. And AGEM is a work by Facebook. SGD, which is the vanilla stochastic gradient descent, and also to have a notion of upper bound on the performance, we compared with MTL, which is the multitask learning baseline, and it assumes it has access to all previous data. So in our first experiment, permuted MNIST, we generate 3 permutations that shuffle the pixels in an MNIST image and track the performance on each task over the course of training. For the first task, different methods obviously are similar. And when task 2 is introduced, like yellow and green curves who belong to naive SGD and EWC start to degrade their performance, while OGD and AGEM are trying to keep their performance at the level of multitask baseline, who sees all the information. So MTL is the purple curve. And moving to task 3, we can see that OGD is performing as good as AGEM, but note that AGEM does keep the actual data, but OGD doesn't. So that was for 3 tasks. Now for 5 tasks, in our second experiment in this benchmark, we reported the classifier's accuracy after training had completed, that is at the end of task 5, and measured the accuracy for data from each of the tasks from 1 to 5. So we saw a similar behavior for OGD here too. So for the second experiment, that is the rotated MNIST benchmark, the training setup is similar to the permuted MNIST benchmark, except that instead of arbitrary permutation, we used fixed rotations of the MNIST images. So on the left, you can see the accuracy of different methods on task 1 after being trained on the second task. So it's just seeing at the forgetting problem. First task is the original MNIST data, and the second task is derived via rotating all input images by 10 degrees. Here for 20 degrees and 30 degrees, and so on to 40 degrees. So we can see that like OGD and AGEM are like very good, trying to keep up with the MTL when the rotation degree is small, but as the rotation degree goes large, MTL is very much better than the OGD and AGEM, but still OGD and AGEM are far much better than the baseline stochastic gradient descent or EWC. In the second experiment on this benchmark, we use 5 tasks and train sequentially on 5 tasks. And so on the right, you can see the accuracy of models for test examples from the indicated class after being trained on all 5 tasks in the sequence. We can see OGD is often the best. And now the third important benchmark in continual learning is the split task. And here we experiment on split MNIST. So for the split MNIST, classes are divided among tasks. So in the first experiment, we have two tasks. Each of them has 5 classes. So each of them is a 5-class classification problem. So the reported values are the accuracy on task 1 after the model being trained on task 2. So again, the forgetting. And different plots correspond to different configurations again. So OGD is the blue one, and we can see that like this is the the first benchmark, the first configuration, and now we also have tested with 4 more random configurations of how to put these 5 classes into class 1. So for different permutations, again, we can see that OGD and AGM are doing a good job compared to the baseline, but still OGD doesn't keep track of data. And even when we go to more than 3 tasks, like 5 tasks, 5 being like training on 5 tasks sequentially, and then and seeing the accuracy of the models for the test examples after being trained on all of this. Here we can see again that OGD does a very good job compared to all others on preserving task 1, task 2, and task 3's knowledge, and also having a good performance on the current task, which is task 5. So this was the first part of the first idea that was introduced. So to conclude, we mention again that OGD maintains a fair amount of accuracy on previous tasks while learning the new ones reasonably well. This is possible without need to explicitly store the previous data. So as some pointers for future works, we still witness some forgetting that may suggest going for higher order of invariant spaces. So OGD just considers the first order derivative or gradients. So one can possibly go higher with higher order gradients. So one difficulty in the proposed method is that the storage scales proportionally to the number of tasks or to the number of examples that we store. So one can potentially maintain only some significant and principal directions similar to principal component analysis PCA. We have seen that all the methods, including ours, fail when the tasks are very dissimilar. Remember the rotation task when the rotation degree was 4t. This calls for much more further research in this problem. And we also want to note that OGD, similar to SGD, is sensitive to hyperparameters like learning rate. So that's potentially many other optimizers, many of those accelerated optimization scheme can be used to stabilize SGD or OGD in continual learning. And we would like to note that OGD has implications beyond continual learning. Whenever you want to minimize the interference of the new updates with the previous parameters, OGD can be a help. And we can combine OGD with representation learning. We really don't need to store the high dimensional parameter of the neural network. There might be some lower dimensional spaces in which tasks are orthogonal, not in this high dimension. So that was the first part, the first idea. And in this talk, we're gonna in the next idea, we're gonna pursue another direction, which is like a natural solution toward continual learning, is to create different pathways per task through the neural network. So here we seek for automatic ways to regularize the training that leads to an organic gating between the task when they are going to do inference, forward propagate or backward propagate. So Dropout is being known to alleviate catastrophic forgetting since 2013 paper of Goodflow et al., where they hypothesized that Dropout is increasing the optimal size of the network. However, After seeing some inconsistent results, they suggested there might be other factors involved. And the effect of dropout in continual learning is also verified empirically by others, such as the synaptic intelligence paper by Zenke et al. After we also observed the surprising success of dropout in continual learning, we also became curious, what does dropout do? And what we found is dropout is creating different gates or pathways for tasks. Therefore, the tasks are interfering minimally with each other. So let's see some empirical evidence for that. The top rectangle is the activation heat map of the 100 neurons of the first layer of a two-layer neural network, MLP. And the top panel is the case of being trained without dropout, but the bottom panel is the case for being trained with dropout. So the first interesting observation is that the activity pattern of neurons of the network trained with dropout is sparser than the case without dropout. Some neurons are very active and some very inactive. This is in contrast to the behavior of the neural network without dropout, where almost all the neurons are very active for all tasks. So the darker color is the more active and the lighter color is the less active neuron. So now if we focus on the behavior of a single neuron of a network with dropout, we see that the neuron is active for some tasks but is inactive for the others. Only a few of them are always active for all tasks. This behavior shows the gating mechanism of the network trained with dropout. The bottom figure shows the activation patterns of task 1 at the two different times. The top row is the case for right after learning the first task or beginning of the continual learning experience, and the second row is the activations of task 1 after learning the final task or the fifth task. So as illustrated, the activation behavior and the gating is fairly consistent and the pathways are preserved. So they are almost like task 1 is directing its forward signals through almost the same signals to this, like similar to the case to the activations after task 5 is done. So the pathways, so dropout is not only creating pathways, but it also keeps the pathways throughout the continual learning experience. So training the network without dropout. So let's see some results empirically. So panel A is for training the network without dropout and learning rate, which is a highly plastic network. So we refer to the cases that the change can happen very easily as a plastic network, in contrast to a stable network who tries to keep its preserved knowledge as much as it can. So the top panel is for permuted MNIST, the bottom panel is for the rotated MNIST, and then the left one, panel A, is training without any dropout or learning rate decay. Panel B, or column B, is training the network with a small dropout probability, it's like 0.25, and the third column C, is the output of the network with high dropout probability, p equal to 0.5. So column A learns new tasks better and faster than the more stable ones, but they also forget old tasks very quickly. You can see like the red curve, which is the accuracy of task 1. The panel A loses its accuracy on task A very quickly, but panel B, which is more stable, keeps the information better, and then the red curve in the column C, we can see that it preserves as much as it can. And this stability is achieved with a small negligible accuracy on the current task. So here, for example, the purple one is the accuracy of task 5, or let's see the accuracy of task 4, the yellow curve. So in the stable regime, they are a little lower than the plastic regime, but this small cost comes with a huge gain in remembering task 1, the red curve. The similar pattern also exists for rotated MNIST benchmark. So dropout training of neural network not only is good for stabilizing networks, but the simple yet effective trick can outperform many existing approaches, including the previously presented one, OGD, HM, and other baselines in the literature. So this is the accuracy of each task after being trained at the end of task 5. So, for example, task 1 is how much I remember task 1. So, to conclude this part, we would like to highlight that promoting sparsity is an elegant and natural way to stabilize the network and reduce forgetting. It exists. The sparsity exists. For example, in human brain, where both structural and behavioral patterns are highly sparse. So, and like the nature stabilize via sparsity. So neural networks should also be able to do that. So therefore, it's going to be a promising direction to improve continual learning algorithm. So I can imagine employing smarter gating methods, from manual gating in some layers to probabilistically enforcing pathways, for example, via generalized dropout, or in a Bayesian way by assuming a cluster-based prior over neural activities, and like using attention models, for example, to attend to the part of the network that is relevant for the task. Anyways, gating mechanism or task-specific pathways is one way to explain the effect of dropout. We hypothesize that this might be related to a more general property, which we will investigate next. So in this work, we explore the catastrophic forgetting problem from an optimization and loss landscape perspective, and hypothesize that the geometry of the local minima found for different learned tasks correlates with the ability of the model to not catastrophically forget. We're gonna divide this part into a few research questions. First, how important a training regime is in continual learning, and how study the role of training regime. And then how we define catastrophic forgetting and how to measure it, and what factors import those that define catastrophic forgetting, and what is the impact of the training regimes realized in question 1 and 2 on these factors. So let's start with the first problem. How important is the training regime? So remember our first experiments in characterizing the amount of forgetting in permuted MNIST. We witness a huge loss in accuracy of task 1 after 4 more tasks being trained. Let's see how a different training regime can alleviate this catastrophic forgetting. So the blue curve is the result of training under a different regime. We set a dropout rate, choose a smaller batch size, employed a large initial learning rate, but decayed it over time with a learning rate decay of rate of 0.4. And with this setting, with this simple setting, some just hyperparameters, we retain the accuracy of task 1 for almost 30% by just slightly changing the accuracy on the current task. So this is huge and worth further study. It's not just dropout. It's much more than that. It's not just gating. It could be much more than that, and we'll investigate this here. To do so, we choose to study training regimes from the view of their effect on the loss surface of the neural network. This could equip us with a fundamental viewpoint to learning dynamics and to training properties. First, we need to have a clear notion of forgetting. Let W represent the parameters of our neural network model, and L1W be the loss on the first task. And the optimization for task ends up at the local optimum W star 1, and task 2 is introduced, and after optimizing for the new loss function, we relocate by a distance delta W. And the amount of forgetting is equal to the change in the loss function between W star 1 and W star 2, which we call F1, and means forgetting of task 1. Mathematically, we define forgetting of task 1 equal to L1 W star 1 minus L1 of W star 2 minus L1 of W star 1. This is our target in overcoming catastrophic forgetting. So our goal is to minimize F1 while having a good L2. So to make this notion of forgetting tractable and analyzable, we use the second order Taylor approximation of L1 around W star 1 to rewrite the forgetting. Since W star 1 is an optimum for L1, the gradient is 0, and we will be left with a second order term that can be upper bounded by the largest eigenvalue of the Hessian of L1 at W star 1, multiplied by the square size of the relocation vector. This upper bound forms our target quantity for analyzing forgetting. To reduce the catastrophic forgetting, we should decrease this upper bound and vice versa. So our hypothesis is that the amount of forgetting in continual learning of a series of tasks is correlated with the geometrical properties of the loss function at the convergent points. In particular, the wider the minima are, the less forgetting happens. So we've seen this bound kind of mathematically. So the details are in the paper. Please refer to that. And now we're gonna intuitively see if this bound makes sense. So let's examine it. Blue and green curves are two loss surfaces for task 1. The red curve is the loss for the second task. So we can see that the first task optimum is sharper. When the first task is sharper, that is the green curve, the forgetting is more because the loss curve can go higher when we stop for the second task. In contrast, the blue curve that exhibits a wider minimum or lower curvature exhibits less forgetting. So that's how the loss surface of first task is important for amount of forgetting. Similarly, we can study the second task curvature. Let's consider two cases for the second task again. The red one is a wider case for task 2, while the orange one belongs to a task with sharper minimum. In the commonly used SGD-based algorithm, we usually stop at an epsilon closeness of the optimum. When the optimum is wider, for example, in the red case, we can stop further from W star 2 or equivalently closer to the W star 1. This corresponds to smaller increase in loss or lower F1 and leads to less forgetting. So in summary, the lower the curvature of the loss surfaces are, the less forgetting happens. Moreover, the forgetting is also clearly a function of delta W. So this means the further you go, or the further you move, the more forgetting happens. So we empirically verified the relationship between the forgetting and the upper bound derived before. The dots represent different neural networks regimes with different training, with different settings. For example, with and without dropout, with and without learning rate decay, so with different initial learning rate, with different batch sizes, and with different random initialization. All of the models have roughly like 90% accuracy on task 2, so they are all good at task 2, and we just measure and draw their forgetting on the y-axis. So we can see that our derived measure has a reasonable correlation with the amount of forgetting, meaning that lambda max 1 of task 1 times the relocation, the size of the relocation vector is highly correlated with the forgetting. So if we can propose methods to bring down this quantity, hopefully we'll incur less forgetting. So here are the set of widely used techniques that are known to affect the widths of the minima as we derived, and as well as the lengths of the path taken by the learning algorithm, or delta W. These observations had been generally made with respect to improved generalization, like following the widths narrow minima, the widths or the narrow minima hypothesis in the neural network generalization literature. But here we're proposing that these techniques have implications for continual learning by widening the loss surfaces. So we also tried to study the bound more deeply. So each row of this figure represents one of those related concepts. The top row shows the evolution of the accuracy and validation sets of each task during continual learning. For instance, the blue line is the validation accuracy of task 1. In the middle row, we show the 20 sharpest eigenvalue or largest eigenvalues, or like curvature. These are associated to the curvature of each task. And in the bottom row, we measure the L2 distance of the network parameters between the parameters learned for each task and the parameters learned for the subsequent task. So, so the two left columns are for the stable and plastic training in permuted MNIST, and the two right columns are for the rotated task. We can see first that the accuracy stays at high levels for previous tasks without accessing to their data, thanks to stable training. And also we can see that the stable training brings down the eigenspectral. So the largest eigenvalues would be smaller in stable training, and that means lower curvature or wider minima. Not only it brings down the eigenvalues, but also make the loss surface or change the loss surface in a way that the local minimas for different tasks are closer to each other compared to the plastic network that the optimization goes further for the subsequent task, but here they're almost close to each other or relatively closer compared to the stable case. So that's the magic of simple simple hyperparameter tuning, or making sure that we are aware of our training regime in continual learning and employing the right amount of stabilization regularization in our training. So here we show that stable network is a strong competitor for various continual learning algorithms. Again, we compared with several baselines that employ complicated techniques, either replay or memory or whatever, but simple, stable training can outperform many of them. And also, while our stable network performs consistently better than the other algorithm, we note that our proposed stabilization technique is orthogonal to other works and can be also incorporated into them. Here we can see that improvement, we can see the improvement of the performance of the existing methods by stabilizing them. For example, stable AGEM works better than AGEM. Stable EWC works better than EWC, and so on. The same figure for all the tasks, not at the end of training. So to conclude this part, I like to mention that studying this problem is still an open question. That how a training regime affects the loss landscape of neural networks. Neural networks are highly over parameterized, millions of parameters, and it's hard to visualize and it's hard to make sense of this high dimensional space. And that's where the magic of the modern neural networks lies. So in order to understand neural networks, we need to understand this loss surface and how the optimization proceeds in this high dimensional space, and that has a direct consequence for continual learning. Studying the effects of other stabilization techniques such as batch norm or the popular meta-learning framework is also an interesting problem. And also, the choice of the network architecture may also have implications for continual learning, may have some implicit bias for continual learning, like convolutional layers compared to the fully connected layers. They might be different for the task of forgetting. And these are highly unstudied in the literature. So In our next idea, we like to explore another problem or another aspect of continual learning, but again through the loss surfaces. So, and we wonder how much previous loss functions are beneficial in alleviating catastrophic forgetting. So to study this question, we approximate the loss function of the previous task with the second-order Taylor expansion around the first task, optimum, and we use them as a surrogate along with the current task loss function and minimize these two together, like the sum of their losses. This way, we don't need to store any actual example like those of replay-based methods, or we don't even need to store any gradients like OGD. So we abstract all the relevant information of the previous task into their approximated loss function. So here is how we write it mathematically. So L1 tilde is the approximated loss of the first task using the Taylor expansion. And as you see, we need the Hessian matrix, which could be computationally prohibitive. Like it's a second order derivative. So it's in an ideal case, it's matrix. And for modern neural networks, it's huge. It's millions by millions of parameters. So therefore, one can use a low-rank approximation instead of the full Hessian. And that's an approximated version of our proposed algorithm, SOLA, second order loss approximation. So, and we decided to directly work with the loss function, or it's approximated in this way. This allows us to perform a theoretical study of continual learning problem. So we've been able to derive sufficient and worst case condition for gradient descent on the approximated loss function that can still minimizes the actual loss function. So under what conditions a second order approximation is a valid approximation for continual learning, and an SGD still minimizes the actual loss if we replace the actual loss with the approximated loss in our optimization procedure. Moreover, this allowed us to do convergence analysis of the algorithms for both non-convex and convex loss functions. So I won't go into the details of these words, but please refer to the paper if you're interested. And as a byproduct, we analytically witnessed the benefit of early stopping for continual learning. So, which was obviously obvious in the empirical studies. So we conduct a comprehensive comparison among our algorithm and several baselines on a variety of combinations of dataset and models. In many scenarios, especially where the learner is not allowed to store raw data or their gradients, the proposed algorithm outperforms the baselines. Empirical evidence validating the importance of accurate approximation of the Hessian is also presented in the paper. So that will allow us to decide at what rate we can approximate the Hessian and still achieve a good accuracy. So remember, we in SOLA prox, we used the low-rank approximation of the Hessian in our algorithm for the loss function for the Taylor expansion. So to conclude this talk, I'd like to mention again that continual learning is an emergent field that is an important building block of artificial intelligence. The ability to learn continually over many tasks, remembering the previous ones while adapting to new ones faster and faster, is a critical milestone towards a real-world intelligent agent. Like if we want to deploy an AGI agent in the real world, we don't want to train the agents over the new task again and again or new tasks. So humans are very good at transforming what they've learned towards new tasks, and not only that, they maintain a good performance, a good level of performance on previous tasks. So if we're gonna deploy AGI agents in real world, we need to make sure they preserve as much as they can. So there are a lot of open problems and interesting questions yet to be tackled in continual learning and catastrophic forgetting. So remember, catastrophic forgetting is only one subproblem in continual learning. There are many more, like task detection, task boundary detection, forward transfer, like the ability to generalize over the new task better compared to the case that we haven't seen any task before, or even backward transfer. When a human agent learns a new task, this information can help the agent to perform better on previous tasks. So the information that the new tasks are providing to the agent are helpful and should be helpful to improve the performance on previously seen tasks. So maybe some instance of them will happen in future again, or they have relevant information. We need to maintain those information. So there is a hot debate in continual learning literature about the benchmarking and dataset. Many believe that simple tasks like rotation MNIST or split CFAR, these are synthetically created continual learning benchmarks. So we need to find real data sets and deploy continual learning algorithms in real data sets. So there is a trending amount of work in those lines to try to create new benchmarks, new data sets for continual learning that allows us to evaluate the effectiveness of catastrophic forgetting algorithm or the effectiveness of the forward and backward generalization. So the other interesting problem is to employ generative models or hybrid models in continual learning in some way. Like generative models are somehow generating data. They are somehow some tools for imagination that could help continual learning. If you imagine, if network is able to imagine, it might be able to better remember data as well. So continual learning or multitask learning is by design a multi-objective optimization problem. So how we disentangle this war or this tug-of-war dynamics between multiple tasks or multiple objectives is a critical problem in multitask learning, in continual learning, and in optimization approach towards machine learning. As we've seen that sparsity and smart gating are important because we've seen that one instantiation of sparsity and smart gating in the world, that's the human. Human's brain is able to do this amount of highly difficult task, and one reason might be the sparse behavioral and structural properties of the human brain. And attention, if we employ sparsity, then which part of the network we should attend for a task? Then using that we can use the highly well developed attention literature into continual learning. So again, representational learning is also an important problem. For example, in OGD, we worked with the raw data, or in all the continual learning, they try to memorize or replay raw data. But but potentially like information in human brains are encoded in some other representation spaces, and that can be used as a regularization or as a replay for to achieve lower catastrophic forgetting or higher forward transfer. One can equip uncertainty and out of distribution detection methods into continual learning, like uncertainty over prediction, like some inference about tasks can help continual learning a lot. And finally, the last but not the least, like continual learning literature is somehow being an empirical field, but this calls for a lot more theoretical analysis and the studies in the field. Like for supervised learning, we have the empirical risk minimization literature that statistically study the machine learning problem in supervised learning case, but that's this kind of rigorous uh, 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 rigorous foundation is highly missing in continual learning literature. So finally, I'd like to mention that continual learning is related to many other fields. Like continual learning by design is a problem of learning over evolving data distribution. When the data is shifted or the distribution is shifting over time. This is also related to the domain adaptation problem where train and test distributions are shifted. So some believe that like meta learning could be a very good framework to formulate and tackle the continual learning problem. And also, continual learning shows itself in many other forms like lifelong learning, incremental learning, online learning, stream learning, multitask learning. There are a lot of related, like on knowledge distillation, there are very related subfields that can be used to bring interesting working ideas into this emerging problem and make continual learning better and ultimately achieve better AGI agents. So thank you for listening to this talk, and feel free to reach out for any ideas, questions, or comments. Thank you very much.
All right, now we will have the Q&A part. Salam Mehrdad, welcome and thank you for this interesting presentation. I don't hear you. Well, it seems that we have some problem here. All right, we're back. Salam Mehrdad, welcome and thank you for your interesting presentation.
Thank you very much for listening to my talk. So let's start the question one by one. I will start from the question that Aryan asked.
Let me display the questions for you and others. Okay, we have two questions about which have some similarities. Let's start with them.
Okay, so yeah. So Aryan asked if does it always happen for each task, for the two tasks to have a space with low error, and how about with more tasks? So first of all, like modern neural networks are over parameterized. They have like millions of parameters, and the number of parameters is like at the order or even larger than the number of data points. In this very high dimensional space, the our intuition about geometry usually fails. And and it's very complicated. Imagine you have like millions of directions to proceed instead of 3 directions in the Euclidean space. And in this weird space, it is believed that like when we overparameterize neural networks to those large spaces, the loss surface is changed so much so that like there are a lot of there appears a lot of local minima, and not only that, like many of those local minima or all of them are global minima. So we like change our hypothesis space and the loss surface in a very complicated way. So and this increasing the number of local or global minimas may make the solutions of two different tasks intersect. Again, now going beyond two tasks, like imagine we have 3 tasks. So the solution of the 2 tasks, that intersection is itself a lost landscape of a different problem. Again, inductively speaking, if still it's over parameterized, and the intersection of this 2 combined loss surface and the third task can be analyzed in this over parameterized regime, then we can find an intersection and proceed this way. So all these were like mostly intuitively, like neural network practitioners and theoreticians are still working on this. And this is somehow an informal belief. Question 2. So Aryan asked, not Aryan, Babak this time, asked about how MTL works and how the intersection. So I will let you read the question.
I think what he's saying is that you could say if there was actually a misunderstanding in the question part, but he says that you are actually training on the hypothesis space for task 1, and in contrast with multitask learning, and he's asking if it will help if we can freeze some more important weights for task 1 to help to maintain the accuracy.
Yeah. So first of all, yes, MTL does that. It's trying to change MTL changed the problem, and it somehow combined the 2 hypothesis spaces to get a combined and integrated hypothesis space to optimize over that. Then, like, I have a feeling that this question has been asked in the earlier part of this talk. So, yes, freezing some more important parameters for for task one helps, and that's like the idea behind regularization-based approaches, including EWC, that uses, for example, the Fisher information matrix to find those important weights. Or there is another work called like uh, mhm, synaptic intelligence, or uh, another card by Rahaf Al-Jundi, that they use the change in the loss, the rate of the change in the loss as the importance parameter, and they use that to regularize the gradient updates. And yes, Dropout also has some regularization effect. So in that sense, uh, uh, Dropout is restricting the info the gradient update. By restricting the gradient update, you naturally uh, overcome catastrophic forgetting by a certain degree, not that much, but definitely when you're not allowing your parameters to change either via regularization or some importance-based regularization, then you're tackling catastrophic forgetting. The important question is how effectively we can regularize this gradient update. So we are allowing to learn a new task, we are leaving some capacity to learn new tasks, but still maintaining the performance over previous ones. I'm not sure if
Right.
I answered your question, but feel free to jump in if you have follow-up.
Right. Yes. If you have any comments, Babak, you can write it in the comment section, and we will get back to it. All right. We have a question about how we do the projected gradient descent.
There was
And
a question by Ahmad. Can we think about hindsight relabeling as a solution for alleviating catastrophic forgetting issues
okay,
in
I
RL
thought
tanks?
we could. Okay, let's go
Actually,
here
yeah, we
first.
can move to the next question because I don't know what is hindsight relabeling. So it's better I don't answer that question.
All right.
Sorry.
Yeah, I was going to put that at the end
Right.
because it was about reinforcement learning.
Okay.
Okay, about projected gradient. Here's a question. You first get the gradient and then project, but there are some problems, namely dense gradient and intermediate parameter structure. As gradient descent iterate can be arbitrarily out of set. Shall we directly optimize over projection?
Uh, I'm sure, and like I believe, and I'm sure that there are more efficient ways than the Bayer OGD that we've tried. So in OGD, we just wanted to showcase the idea of projecting the gradient predictions, and going over there. So like even I've tested this OGD in a convolutional neural network. It didn't work as expected. So that might be some issues about this same comment. So potentially some gradients are going to zero, or some projections are giving us
I think we have lost the voice. Excuse me. Okay. Okay, I think we are back now. For some minutes, we have lost your voice, Mehrdad. Can you go back a little and continue?
Yeah. So I was saying, sorry. I think my internet was dropped. Again, I will say what I said. I was saying that yes, OGD is working with the bare projections, but I'm sure that there are better ways to leverage those projections in continual learning. For example, when I was trying this idea on convolutional neural networks, I've seen that some weird behaviors of the projected outcome, and I didn't get time to study that. So hopefully there are smarter ways, and this OGD, these gradients of the are just input to that procedure. So potentially we should be able to manipulate these projections to get a better sub object for continual learning.
All right. Next question. Is there any biological intuition for solving the forgetting problem in the deep neural networks?
Yes, actually, like for example, the sparsity-based solutions are inspired by the biological phenomena. Like human brains are highly sparse. Like the sparsity rate are the order of like 10 to the minus like 5 percent of the, like for example 10 to the minus 4 of the input activations are active. So this amount of sparsity is huge, and actually the size of brain is also huge, but the sparsity is also huge, and this sparsity naturally comes with some natural way to alleviate catastrophic forgetting. So that's one thing. uh, uh, and like, not saying that this is natural, but like replay based method, memory based methods who replay something, they are also similar to how human brain works. Like when we sleep, it's believed that when we sleep, the what has happened in the day is being replayed, and that's allows human brain to memorize, to learn what they have experienced in the day. So they believe that sleep is a very important uh, part of uh, part of learning. So, and that might be related to the replay, and like going even in more abstract things, when we try to memorize things, like we take notes and we read them again like a few days later. That's how our brain is supposed to work, to memorize things. So that might be one explanation.
All right, let's go a bit faster on the next questions. Incremental learning, such as few-shot class incremental learning, are always suffering from the same problem. Have you any suggestions for solving the forgetting problem in class incremental learning?
Okay, so when they talk about like continual learning, they usually divide it into a few parts, and one of them is this class incremental learning. There are like cases like domain incremental learning, and there are like just normal continual learning when they add new heads per task. So all the ideas that I've talked can be applied to this class incremental learning, potentially with a slight change. So there are a few surveys that have talked about, especially this class incremental learning. I guess one of those surveys that I introduced also have that. So yes, this is a known problem, and people are already are already working at this.
All right. How weight decay affects forgetting and stability?
Yes, so like weight decay by essence, by design, is a regularization based approach, and it has some effects in catastrophic forgetting. But the EWC paper, the Overcoming Catastrophic Forgetting in Neural Networks, they have compared it experimentally that like the EWC outperformed the weight decay regularization, the L2 regularization. And then after that, and after those early days in continual learning, nobody again bothered to compare with weight decay because like most SGD based, most naive SGD comes with weight decay as well. So it has a very little effect. It has effect, but it's very little.
All right. What do you think of using curriculum hardness of samples to train in order to reduce catastrophic forgetting?
Yes. So this is a very good idea. Like there are some similar ideas in recent publication. For example, one paper at ICML, I guess this year ICML was published, and they were finding some samples. Like they were filling the memory for the AGEM with some samples, with some of the samples. They were selecting some samples that are best for their forgetting task. So this is a very good idea, and people are starting to think about what are the good samples to use in a replay or other or regularization based approaches.
All right, we are officially out of time. If you have time, Mehrdad, we can continue questions.
Yeah, I have time. Yeah, we can continue.
All right. What if we use sparse to sparse methods like lottery ticket or soft threshold reparameterization?
Mm-hmm. This is indeed another good idea. Yeah, definitely. Lottery ticket hypothesis and their its followers, they bring a new viewpoint towards sparsity, and as we saw in the dropout idea, sparsity is something that that helps continual learning. So I would say this is very promising direction.
Right. Well, I think it's a question regarding one of the slides, if you know what it is.
Yes. So, like Dropout has a regularization view, and like any regularization, like what does regularization do? Regularization is limiting or restricting your hypothesis space or the directions that you're gonna search for the optimum parameter. So when you do regularize, you're limiting your learners. So that might be one reason that we see a little drop in the performance.
All right. How is continual learning different from incremental online and lifelong learning?
All right, they are very 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 similar. I would say. Like for example, in online learning, some like people like mostly theoretician work on online learning, and they care about, like for example, measures like regret bounds, and they also care about like fast adaptability to the new task. And again, incremental learning is the same. So the same for lifelong learning. So you can find very very similar ideas in all these papers. So, and the difference is so little that, like for example, lifelong learning can be like alternatively or exchangeably used instead of continual learning.
All right. Okay, I have a question myself about OGD. If I understand your presentation correctly, you use the gradient descent for task 1 at the end of its learning, right? And use it for projected to find a space which will keep the gradients the same, right?
Yes.
And the question I have is that after doing some steps on the task 2, you will have different gradients on task 1, and the method that you fix the space, it's kind of like supposing that it's a linear problem where you where the gradient is the same on every point of the space, because after some steps on learning task 2, you now have a different gradient on the loss of task 1, if I understand correctly. Actually, I have some problem understanding the complete picture of what is the rationale behind projected gradient descending this way.
Yes, very good question. So the assumption is that, like, again, because the network is over parameterized, you can find a new optimum near the optimum of the previous one. And then, because of this is happening in a small neighborhood, we assume that the gradients are still valid. Like the gradients in the new optimum are equal to the gradients on the previous saved point. So we use them as a surrogate of the gradient space in the new location. So that's again an assumption. And when we go very much further from the previous task, those optimums are potentially, those gradients are not a valid gradient for the task at hand. So that's potentially a failure point for OGD.
All right. Thank you, Mehrdad. I think we can conclude the session here. If you have anything to say.
Thank you very much. I really enjoyed the questions. There were a lot of good ideas and questions in the questions, and they're all very good questions. So I appreciate your time, and again, thank you for listening to my talk.
All right. Thanks, everyone. We will be back at 11 by the presentation of Mehrdad Madadi from the University of Autònoma de Barcelona on deep learning advances on human pose and shape estimation. Goodbye.
Tamam.